Hello team, in this video we're going to talk about Apache Hadoop and how it implements the MapReduce paradigm. So here we have a view of the cluster model assumed by Hadoop. So Hadoop came before the move to the cloud and before cloud providers started using remote storage. So Hadoop assumes that servers have local compute, memory, and storage. This is why we see these disks over here. And then there are many racks, and then the racks are interconnected by top of rack switches. And Hadoop supports thousands of nodes to handle large volumes of data. And it also assumes that there are lots of disks to store these large datasets to support replication and speed up input and output. A Hadoop deployment has a main node and worker nodes. In our cluster, the main node is the node that we SSH into, and the other three machines that we don't access directly are the worker nodes, and they run the MapReduce jobs that we submit. As the name implies, MapReduce has processes to run the map code, some processes to run the reduce code, but the platform also provides the code to do the split of the input data, the shuffle, and the merge. So we don't need to write this code, we get it from the platform, and also the platform takes care of connecting split to map and then map to reduce and then reduce to merge. We don't need to care about networking, and we also don't need to care about transmitting data. Also, Hadoop takes care of spawning map and reduce instances during the shuffle. It monitors that the map and reduce instances are running okay, and it detects failures. And if a failure is detected, it automatically restarts the processing that were impacted by that failure. So we don't need to care about some server crashing while our job is running. And because MapReduce processes might run on thousands of nodes, it might actually happen that a server or a disk fails during the execution of a job. So we don't need to worry about this. Hadoop is going to restart the process for us. And some of the data will be processed twice because let's say a map instance crashed. So the map instance was processing some data and then it crashed. So Hadoop will detect this crash, restart the job, the map instance at another server. And then the new map instance will process the data for the failed map instance again from the beginning. So mind you, not the whole data, just the one for the map instance that crashed. We're going to process that part of the data again. So the cool thing about MapReduce is that we get all of this scalability and monitoring and resilience for free. We basically need to write the map and the reduce classes, and everything else is provided by the platform. A key component in Hadoop is HDFS, the Hadoop Distributed File System. So Hadoop handles massive amounts of data, and data is managed by HDFS. So HDFS is a file system designed specifically for Hadoop's needs. HDFS has two types of nodes. There's a name node and multiple data nodes. So HDFS splits files into large blocks, and the default configuration is 128 megabytes, so these blocks are rather big, but some deployments are suggesting 256 megabytes, so they make the blocks larger to speed up processing. So the data nodes store these blocks. So here we have three data nodes, data node 1, 2, and 3, and they store blocks. And each file has two blocks. So data node 1 is storing blocks B1 and B2 from file 1, and it's also storing block 2 from file 2. And data node 2 is storing block 1 and block 2 from file 2 and block 2 from file 1. And data node 3 is storing blocks 1 for files 1 and 2. So we see that the blocks are replicated. For example, file 1 block 1 is stored in data node 1 and in data node 3. And we see why this is in a bit. HDFS also has name nodes. So the name node indexes files. And each file has a table of blocks. And then the blocks are mapped to multiple data nodes. So for example, file 1 block 1 is stored in data nodes 1 and 3. File 1 block 2 is stored in data nodes 1 and 2, and so on. HDFS uses replication to achieve high resilience. So each block is replicated 3 times in the default configuration. And this allows HDFS to rebuild data if a disk fails. So if a server fails or if a disk fails, the data that were stored in that data node will be copied, duplicated on a different data node so that we keep 3 replicas all the time. And Hadoop knows about cluster hierarchy, so it knows on which rack each server is located. And it uses this information to distribute file blocks across different failure groups. So some servers are in the same rack, so they share the power supply, and they share the top of rack switch. So if there's a power outage in a rack or a failure in a top of rack switch, all replicas in that rack will go down. They will be inaccessible. So to avoid these failures impacting HDFS, Hadoop distributes blocks across servers that are in different racks. So if a rack fails, we still have replicas in other racks and we can create new copies to keep 3 replicas online. HDFS and MapReduce are tightly linked, and we can exploit this information to improve performance. For example, a programmer can split data to fit the block size. So the block size is 128 megs. So what we can do is we can store many records inside a single block. And then whenever we read that block, we can process, many records from one disk read. One problem is that because the blocks are rather large, if we don't store a lot of data in a block, we might waste space. For example, if we store a book chapter, which is a few kilobytes, in a 128 megabyte block, we're going to waste a lot of disk space. So the block is like huge, 128 megabytes, and the book chapter is like 10K. So it's very small and most of the space in the block will be unused. So what we need to do is put a lot of records, like many chapters from many different books inside the block so that we make good use of the space. So here we have 2 examples. There's block 1 with many figures and then block 2 with other figures. And there's some space at the bottom. I had, this little black square over here that's wasted because we didn't have any figure that fits in that little space. But it's only a small fraction of the block because we can keep adding figures until we get very close to the 128 megabyte limit and can't add any additional figures. The HDFS file semantics are optimized for MapReduce. So MapReduce reads data sequentially, and HDFS only has read and append operations. So you can read a file, you can add data to the end of a file, but you cannot modify existing content. So there's no write operation on top of existing data. And one last important point is that Hadoop tries to collocate data and computation. So whenever we're running a MapReduce job and Maps is going to read some data, Hadoop tries to place the map instance on the data node where the data is stored. If we can do this, then the map instance can just read the data from the local disk without using the network. So that's good. And this benefits from replication. So for each block, we have 3 data nodes where we can start that map instance and not have data go over the network. So this image I showed you before is not quite true. So with this additional information about HDFS, we now understand that the data is actually split in multiple blocks, and these blocks are spread across many different data nodes. So when a MapReduce job starts, some of these blocks will be located together with the map instance already on the same server. So no data goes over the network. We just read the data from disk, and then map can start processing it. So here I have 2 of these cases, and of course we can do this in all cases, so some blocks will need to be transferred over the network, but not all of them.